Welcome to the presentation of An Observer for the Electrically Heated Vertical Riker Tube with Nonlinear Heat Release at the Virtual IFAC World Congress 2020. This paper is based on a phenomenon known as thermoacoustic instabilities, which one finds in a range of different combustion systems. The phenomenon is caused by a positive feedback mechanism between heat release and sound waves, i.e. acoustic perturbations, that leads to a self-sustained limit cycle. The amplitude of the oscillations can get very high and may damage the engine. The extent of the damage can range from being an extra source of wear and tear to destroying the engine within a short amount of time. To study this phenomenon in the laboratory, a setup known as the Riker tube has been devised. This is probably the simplest system that can exhibit thermoacoustic instabilities. Essentially, it consists of a tube open at both ends and a heating element. To generate thermoacoustic instabilities, the heating element must be placed in the lower half. One should note that it is possible to have horizontal Riker tubes, but then a mean flow must be imposed externally. We consider in this paper the Riker tube with electrical heating. In combustion systems and the original Riker tube, the heat source is a flame, but these can be difficult to model in practice. We will in this paper be concerned with observer design to estimate the pressure, velocity and heat release in the Riker tube from a pressure measurement at the lower boundary, as shown in the figure. For this objective of observer design, the paper referenced here gives a good foundation for the observer and also possible controller design for the Riker tube. An observer for the electrically heated vertical Riker tube is derived in this reference. They base their design on the PD-ODE model of the former reference and apply the backstepping method to design the observer. However, the heat release from the electrical heater, which is in reality nonlinear, is linearized in their design. For the approach considered here, we also use a linearized PDE model for the acoustics. However, we decide to keep the nonlinearity in the heat release, so these important nonlinear dynamics are not lost. Our design approach can be summarized as injecting the measured pressure from the lower boundary in such a way that global convergence can be proven. Now we recap the physical principles our model is based on. The first equation for the distributed acoustic dynamics is the linearized momentum equation. The second PDE equation, which also describes how heat release impacts the acoustics, is the linearized energy equation. Here the delta denotes the Dirac delta function, i.e. the heat release is modeled as a point source at position z0. The boundary conditions at z equal to 0 and z equal to L are modeled via acoustic impedances. For the electrical heat release, it is based on King's law, which states that heat release rate is proportional to the square root of the local velocity. With air flowing past the heating wire, a boundary layer forms. This can be approximated as a first-order filter with time constant tau. These two effects together contribute to the following dynamics of the heat release rate. So why is it valuable to keep the nonlinearity in the heat release model rather than linearizing it? A qualitative feature that is typical of thermoacoustic instabilities is limit cycle behavior, as shown in the diagram. To fully capture it, one needs to retain the nonlinearity. One challenge keeping the nonlinearity brings is the fact that it is non-Lipschitz around the origin. From simulations of the velocity, we see this singularity point, represented by the red line, is crossed in practice. This fact makes it difficult to apply established observer design methods to this system. Before the observer is designed, the acoustics are written in Riemann coordinates, and the domain is folded around the point where the heater is placed, represented by the ODE with state x inside the box. Also, the PDE spatial domains are normalized to be between 0 and 1. As the PDEs are simply transport equations, i.e. simple delays, and the ODE is self-stabilizing when there is no interaction from the acoustics, the most basic observer one can make is to simply inject the measurement at the boundary, multiplied by the reflection coefficient D. This reflection coefficient is calculated from the impedances, and we assume that the absolute value of D is less than 1. Although this works surprisingly well for certain cases in practice, one can identify a potentially destabilizing feedback loop, color-coded with red in this diagram. Because of this possible instability, one has to go a bit further if global convergence is to be proven. Consider first the boundary circled here, which is the source of signals that become the measurement y after a time delay. Next, consider that this boundary also receives the ODE state as one of its constituent signals. The difference is that the signal becoming y contains this V2 signal. Using these observations, the observer is made by reconstructing this boundary circled in blue with the known signals. For details, consult the paper. We state now the main theorem of the paper, which asserts global convergence of the observer. Consider error states defined and initialized as follows. Then we can state that the observer guarantees convergence of the estimates to the true state, globally and asymptotically. An overview of the proof is now given. This diagram shows the structure of the error system. It is a cascade system with the convergence of x tilde and hence u2 tilde v1 tilde, depending on v2 tilde, which again depends on u1 tilde converging. We define a signal G that summarizes u1 tilde and v2 tilde as an input to x tilde. This allows us to bound the dynamics of x tilde by this inequality. Because u1 tilde goes to 0 in finite time, v2 tilde satisfies the following after that. From this, we can state that v2 tilde of 0 is related to past states via this equation. Since the absolute value of d is smaller than 1, v2 tilde vanishes exponentially, and hence g is bounded and vanishes exponentially as t goes to infinity. We define now a linear system in xi tilde as follows. Because xi tilde is input to state stable with respect to g, the following bound can be asserted. Also, because of the initial conditions of xi tilde being the same as the initial condition of x tilde, we have that x tilde is smaller than or equal to xi tilde, and the theorem is proved. We state now a minor result of the paper pertaining to cases where the reflection coefficient D is unknown. This is an important case in practice, as the thermoacoustic instabilities are sensitive to the boundary acoustic impedances, and it is difficult to know the value of these parameters exactly. Assume the reflection coefficient is estimated by a d hat, which has absolute value less than 1. Then we can show that the estimation error of our observer remains bounded. For the proof of this result, again consult the paper. Now we are at the final part of the presentation, where we present some simulation results. 3 observers are compared. These consist firstly of the observer from the paper, the trivial observer, where measurement is injected at one boundary only, and thirdly, an observer using backstepping gains from the reference paper, but with a nonlinear ODE model. These 3 observers have been tested in 3 simulations. The first of these is a standard thermoacoustic scenario where all parameters are assumed known. The second simulation is the same as the first, except the reflection coefficient is assumed unknown but estimated by a d hat. The third simulation is a stress test, where the observer's response is tested for extreme parameters, chosen to make the possibly unstable feedback in the trivial observer discussed previously unstable. So firstly, from the general simulation, this plot shows the heat release estimation error for the three observers for a small part of the first simulation. Here the trivial observer and observer using backstepping gains have better performance than the observer from the paper. As you can see, those two observers converge almost immediately. However, the observer from the paper's convergence can be seen to be asymptotic, as the main theorem guaranteed. The equivalent plot is shown for the simulation where the reflection coefficient d is unknown. All observers have bounded estimation errors in this simulation scenario, but the observer from our paper has the smallest error, as can be seen. The backstepping gains helps the observer using them a bit, as the error from that observer is a bit smaller than the one from the trivial observer. Lastly, a plot of the estimation error in the OD state of the observers when extreme parameters are applied is shown here. For this simulation, we experienced some numerical errors with the observers using backstepping gains, so it could not be shown in the plot. The parameters were chosen to give an example of a case where the possibly unstable feedback loop in the trivial observer, which was highlighted earlier, would come into action. As can be seen, this pushes the trivial observer far off the correct estimate, but the observer we proved convergence for retains its convergence properties and converges asymptotically despite these extreme parameters. So, in conclusion, what conclusions can we draw? The observer derived has certain advantages, such as having provable global convergence for all system parameters. Also, as we saw in the simulation, it is more robust to modeling errors in the boundary conditions than alternative approaches. However, it also has some trade-offs. The reconstruction of the unmeasured boundary needed to guarantee convergence can negatively impact the observer by slowing down convergence. This was clearly seen in the first simulation plot, where the other two observers converged much faster. Also, the design features no gains or tunable parameters. Okay, so for future work, it would be interesting to test the observer against a more realistic flow model in simulations. Also, it would be interesting to test the observer in experiments. Also, an observer for a Riker tube with a flame could be interesting to investigate. Thank you very much for listening to this presentation.